Welcome to my channel. This video is mainly useful for those who are all preparing for NET, SET, GATE examination. So those who are all prepare for all this type of exam, this video is too helpful to them. So in this video we are going to discuss about 2D geometric transformation. Mainly here we are going to discuss about translation, scaling and rotation. These three are called as basic transforms. In 2D geometrical, translation, scaling and rotation are called as basic transformation. Okay, so you should know these three are basic transforms. Okay, so you are new to my channel, subscribe my channel for further update, and also if you want to get any information, access it based on the playlist. Okay, that should be useful to you, and don't waste your time to see remaining things. Okay, so before going to see all those things, okay, this is important. Maybe it should be asked in the net set exams. Okay, that's why I will bring this to the first case. Okay, and you know about remaining things in later, and also you know the meaning of it. Okay, we can categorize the transformation in three types. One is rigid, another one is similarity, another one is affine. Okay, so what is rigid? The combination of translation and rotation is known as rigid transformation. Okay, it is used distance preserving. Okay, there is these two operations or these two transforms are related with distance. Okay, then next one is similarity transformation. Okay, it's a combination of translation, rotation and uniform scaling. Okay, that is known as similarity transformation. It is used angle preserving. Okay, it's mainly for angle preserving. Then affine transformation. Okay, it's a combination of translation, rotation, scale and shear. Okay, when we are combine these four transforms, okay, that is known as affine transformation. It is mostly used for parallel preserving. Okay, parallelism. Okay, whenever we want to preserving the parallelism, that time we can use the affine transformation. Okay, so whenever we can use the set theory to represent these three classes of transformation. Rigid is a subset of similarity and similarity is a subset of affine. Okay, by default, rigid is a subset of affine. Okay, it should be applicable. Okay, by default, it should be applicable. Okay, I think so. When you see these things, you can say whether it should be subset or not. Okay, rotation, translation and rotation is available in similarity and also affine. Okay, and also in affine. That's why we can say rigid is a subset of similarity and similarity is a subset of affine. Okay, by default, rigid is subset of affine transformation. Okay, first let's see about translation. Translation, it's related with repositioning the object. Okay, translation is used to repositioning the object. Okay, for example, maybe our object in the original position, there is we can mention the original position as P1 and give a pixel point as 1, 1. Okay, here I gave an example. Okay, that's all. So P1 at the location of 1, 1, and I want to move that object to the new position 4, 6. Okay, I want to move that object to the new position 4, 6. Okay, how we can do it? Okay, we can move the object using the translation distance. Okay, there is a need to add the translation distance with our original position. Okay, and the translation distance represented using tx and ty. Okay, tx in x-axis, okay, ty in y-axis. Okay, so in tx we are giving some value to tx. Okay, that should be a constant value. Okay, we are assigning some value, and based on that value, the object is repositioning. Okay, so common formula used for translation is to find the new position in x coordinate is represented as x dash, and that's equal to x plus, there is original position, that is initial position, x plus our translation distance tx, and new position at y-axis, that is y dash equal to y plus ty. Okay, that is translation distance in y-axis. Okay, so based on that only we can get the new position. Okay, let's see an example. Okay, our object at position P of 1, that is the location of 1 comma 1, and I want to repositioning the object at location P of 2, that is 4 comma 6. Okay, that is 4 comma 6. Okay, now we are deciding the tx and ty. Okay, translation distance tx and ty, it's a pair. Okay, always we are giving the value for tx and ty. Okay, so current position of x is 1. Okay, but x dash should be 4. How we can move 1 to 4? Okay, when I add 3 with the original position, okay, automatically I can get 4. Okay, 1 plus 3 equal to 4. So current tx value equal to 3. Then ty, actual position is 1 in y position, y coordinate. Okay, but the new position is at 6. Okay, when I add 5 with the y, automatically I can get a new position 5 comma 5. Okay, so now we are considering ty equal to 5. Okay, so likewise we can decide the translation distance. Okay, whenever we can represent in terms of matrix, that is, this formula can be represented in matrix. Our new position x2 and y2, that is x dash and y dash. Okay, in matrix format I use several different terms, that's all. x1 y1 plus tx ty. Okay, x1 plus tx y1 plus ty. That is x1 and y1 are original position. Okay, so the translation pairs tx and ty is called as translation vector or shift vector. Okay, the alias name of translation distance pair is translation vector or shift vector. Okay, let's see the another 2D transforms, scaling. Okay, translation is used to repositioning the object. Scaling is used to alter the size of an object. Whenever we want to alter the size, that time we can use the scaling transforms. So scaling, how we are going to perform the scaling? Okay, here we are using the multipliers. Okay, here we are using the multipliers. In translation we are using the addition. Okay, we are using the addition. Here we are using the multiplication. Okay, and we are using the multiplying coordinates values sx and sy. Okay, in translation we are using tx and ty. Okay, here we are using, that is translation distance. Okay, here we are using sx and sy, and already we told already I told to you that's a multiplication. That's why our new position x dash equal to old position into sx. Okay, and y dash equal to old position into sy. Okay, look like tx and ty, sx and sy are some constant values. Okay, sx and sy are some constant values. Okay, whenever we are trying to represent in terms of matrix. Okay, the new position x dash and y dash can be represented using two-dimensional matrix sx 0 0 sy into x comma y. Okay, this matrix representation, that is, we are going to multiply it sx into x plus 0 into y. Okay, by default we can get the formula x into sx. Okay, so this is the way we can get the formula also. Okay, so whenever we can go with the representation of matrix, okay, that should be represented like this. Okay, so this scaling is used to alter the size of an object. Okay, automatically it's alter the size. Okay, okay, in red color. Okay, the red background rectangle is our original image. Okay, I am going to scale it and scale it. Okay, and the newly scaled square, okay, is appeared in the top in blue background. It's in blue background. Okay. Okay, how we are scale it? Okay, that is when I say sx equal to 2. Okay, there is a need to multiply 2 with all the x coordinate. Okay, when I say sy equal to 4, okay, there is scaling factor sy equal to 4, there is a need to multiply all the y coordinate with 4. Okay, then we can get the newly scaled object. Okay, so let's see an example. Here, okay, whenever we are trying to draw the rectangle, okay, there is a need to start it from this point, move towards 3 comma 1, then 3 comma 2, then 1 comma 2, then 1 comma 1, then only I can get the rectangle, okay, or square, whatever may be. Okay, then only I can get this object. Okay, so there is a need to scale all these positions. Okay, there is a need to scale all these positions. Okay, so let's take an example, Sx equal to 2 and Sy equal to 4. When I multiply with x and y coordinate, 2, 1 into 2, comma 1 into 4. Okay, so 1 into 2 equal to 2 and 1 into 4 equal to 4. So our first position, okay, this position can be placed at the location of 2 comma 4. Okay, and the next one is this coordinate. Okay, we are going to scale this point. 3 into 2 equal to 6 and 1 into 4 equal to 4. So our next position is scaled here 6 comma 4. Okay, then likewise 3 comma 2 and 1 comma 4, it's become 6 comma 8 and 2 comma 8. Okay, likewise we can get this scaled object. Okay, always the scaling is expressed in relation to origin. Okay, probably we can scale it using the origin. Okay, so okay, whenever we want to preserve that, okay, origin, we should perform the operation like this. We can preserve it. Okay, that is, the coordinate should be based on the origin. Okay, first thing, there is a need to translate it, then scale it, then translate it. It is commutative. So whenever change this order, we can't get the output. Okay, expected output. Okay, so the order should be translate, scale, and translate. Okay. Okay, let's see one example. Okay, when I scale, when I have the original object like this, okay, when I scale like this, that is, when I change my x-axis as -1, automatically our shape can be reversed, mirror image. Okay, and also when I change it in y-axis, then it's become look like this. Okay, so whenever we want to get mirror object, there is a need to, based on our need, either we can scale it in the x-axis or in the y-axis. So automatically we can get the mirror object of our original object. Okay, so few of the things can affect the size. Okay, affect the size of our object. Okay, so whenever we can give Sx equal to Sy. Okay, scaling factor Sx equal to Sy. Okay, it's known as uniform scaling. Okay, it's known as uniform scaling. Okay, when Sx is not equal to Sy, that is called as non-uniform scaling. Okay, that is called as non-uniform scaling. Okay, so whenever we can go with uniform scaling, okay, the mesh, that is enlarging size should be similar. Okay, that is whenever we can scale the square, once again it's become a square. Okay, in our example, when I scale the rectangle, it's become square. Okay, that is because of non-uniform scaling. Okay, in our example, my Sx value is not equal to Sy. That's why I got this type of scaling. Okay, that is rectangle become square. Okay, so whenever we have same value, that's called as uniform scaling. Okay, when it's not equal to same, that is called as non-uniform scaling. Then when Sx and Sy are less than 1, okay, the size should be reduced and objects are moved closer to origin. Okay, Sx and Sy are less than 1, automatically the size should be reduced and object moves closer to the origin. When Sx and Sy are greater than 1, the size is increased and objects moves further from the origin. Okay, automatically it's move away from our origin. Okay, when we can give Sx equal to Sy equal to 1. Okay, Sx equal to 1 and also scaling factor, all this scaling factor are 1. Okay, there is no change in the size. Okay, there is no alteration in our size. Okay, okay, let's see here. We are scale it. Okay, we are scale based on the fourth case. That is Sx and Sy are greater than 1. So automatically the size is increased and the object also far away from the origin. Okay, see here. The size also increased and also this is, maybe we are consider this is a pivot point. Automatically the origin is moved far away from our origin. Okay, okay, that's all about scaling. Now we will see about rotation. Okay, it is used to repositioning along with circular path. Okay, so whenever we want to reposition along with the circular path, that time we can use the rotation. Okay, okay, so based on the angle, okay, the object should be repositioned. Okay, maybe the object in this angle, when I want to reposition it, just change the angle, that's all. When the values are positive, okay, the rotation is counterclockwise. The values are negative, the direction is clockwise. and we are using this matrix for this.